and welcome to space. And this month we have a unique chance to visit this place behind me, the Avio rocket factory just south of Rome, where engineers are producing the next generation of carbon fiber European launchers. It's rare to get the chance to film in one of these places, so let's get down there, meet the team and find out what's new. This is one of the very few space rocket factories in Europe, the place where the lightweight Vega launcher was born and where the rockets of the future are being created.
This
is the Vega rocket factory. The casings of the first, second and third stages of the launcher are made here. These casings constitute the load-bearing structure of the motors. Here in this building we start from the raw materials. The rubber and carbon fiber comes in and the rocket casings come out, ready to be loaded with propellant.
Most big space rocket bodies are made from metal, but Avio uses carbon fiber for the Vega, and it does so with a unique patented winding technique. The goal is to have maximum bang for your buck.
The key parameter in this design is its lightweight, because obviously a rocket needs a lot of power to get into orbit, but also has to be as light as possible.
5, 4, 3, 2, 1, top.
Just watch a launch and you can see what Vega can deliver. Solid propellant rockets like this can't be throttled back once ignited, but they offer enormous thrust right off the launch pad.
It's like extremely fast and quick rocket to lift off because it's very light. It's relatively light with respect to the thrust that it gets at liftoff. So it is really like a tremendous emotion and impression that you get.
Vega rockets may shoot off the launch pad, but building one is a slow and careful process. It takes a year to go from raw materials to launch. And the first step is to use a kind of giant tube-shaped mould called a mandrel.
To make a rocket motor in carbon fiber, you start with a piece of equipment like this. We call it a mandrel. It's made of many metal pieces assembled together, and on this rotating part of the machine, we wind the carbon fiber. During operation, a rocket motor reaches over 3,000 degrees centigrade. So to protect the structure from these high temperatures, we fabricate this thermal insulation, which is a very thin rubber, and that's the first thing applied to the mandrel. Then we start with bobbins like this. This is pre-impregnated carbon fiber with epoxy resin, which is an Avio patent. And with this material, about 5,000 kilometers worth of this filament, we wind the carbon fiber structure onto our mandrel.
Avio has just used that carbon fiber winding process to create the P120C, the largest rocket engine of its kind ever made. The P120C is important as it will be the first stage of a new, more powerful version of Vega called Vega C. This, the first one made, just passed a static fire test at Europe's spaceport in French Guiana. The same engine will be used in the forthcoming Ariane 6 in a drive to head off competition from India, China and the US.
In an aggressive manner, we are trying to make things more and more competitive. One of these examples is the joint solid rocket motor that we are developing across the two programs, the Vega C and the Ariane 6, the P120C solid rocket motor, that enables the possibility to harmonize resources and to have the same motor serving the Vega C as a first stage, as well as the Ariane 6 in both configuration as a strap-on boosters.
With the first Vega C launch planned for 2019, there's another effort underway to upgrade the rocket's upper stage. This is the part of the rocket that actually flies through space and delivers the satellites into the orbits that customers have asked for. It's the only stage that uses liquid fuel, meaning it can be turned off and on again, unlike the solid propellant engines.
In particular, on Vega C, we developed the fourth stage so that it can carry satellites with a much larger mass compared with Vega now, and it's capable of restarting several times. This allows a lot of flexibility in the new launcher, which can launch satellites from the very small CubeSats, weighing just a few kilos, to those weighing 2,500 kilos, which is very big for our launcher.
With the lightweight Vega, mid-sized Soyuz and heavyweight Ariane 5, ESA's range of launchers can now reach any orbit from French Guiana. And this youngest member of the family continues to make its engineers' hearts leap every time it flies off the launch pad.
The first flight was an unexpected success because it was our first experience of this. So for us, it was very surprising and beautiful to see that. From the first flight, the performances were excellent. So it was just really wonderful to see it.
The power that comes out from inside the engine, both in terms of the flames coming from the nozzle and the deafening noise surrounding the launcher and the engine, is really exceptional. And the first time, it's like your first love. You'll never forget it.
And now to the part of the show in which we take your questions about the universe and put them to the experts using the hashtag #AskSpace. And we're here inside the Avio rocket factory with Giorgio Tomino from ESA. Giorgio, we had a question from Veronica Remondini. She would like to know to what extent we're introducing this concept of reusability into rockets in Europe.
Yes, in fact, we are already working on reusability in Europe and in particular in ESA since several years. I go back to the successful mission performed by Vega on the fourth flight with the IXV re-entry technology demonstrator, where we have tested in flight all the critical re-entry technologies. And in addition, in the longer term perspective, when we talk about Vega E and the investment we are doing to develop the LOX methane engine, which is intrinsically reusable, we could think as the longer term picture to bring down not only the re-entry module, but also the orbital service module, so the complete stages to be relaunched for the next flight.
We also had a question from Ed Bertoni, who would like to know whether there are any alternatives to combustion for rocket flight now.
There are motors that are more efficient than those using chemical propulsion, and I refer here to nuclear propulsion, solar thermal, electric propulsion, and even more futuristic like laser propulsion, solar sails, and so on. The problem is that they lack thrust, and when you want to lift off from ground, going against the gravity, then you need a big thrust, and the big thrust can only be given by chemical propulsion. Therefore, for space rocket applications, I see them not applicable today.
Thanks very much for that insight. Fascinating stuff. Send us your questions about the universe using the #AskSpace hashtag, and we'll try to answer them. And you can follow other space news on Euronews.com.